Hey, it's Mr. Krieger. We're going to be doing lesson 5 in Unit 10, more on circles, lengths involving chords, secants, and tangents. So please make sure you have the lesson available to you. All right, so lengths of chords, segments. Now, we've seen a diagram like this before where we were looking at the angles in here and the arc measures in degrees. Now we're not going to look at that part, but the lengths of these parts of the chords. See, this whole thing is a chord from C to D, and this whole thing is a chord, but they're in parts. There's the part that's A, there's the part that's B, there's the part that's C, and there's the part that's D. Okay, so in the diagram below, chords A, B, and C, D intersect at point E. That's like this diagram. The product of the measures of the segments of one chord equals the product of the measures of the segments of the other chord. So let me show you what you'd be doing. It's a very simple formula. It's simply two parts multiplied together times the other two parts multiplied together. In this particular example, it would be the part that's A times the part that's B equals the part that's C times the part that's D. In other words, you take the two parts from the same chord and you multiply them together. You take the two parts from the other chord and you multiply them together. So like this whole thing is one chord, you multiply its parts together. This whole thing is another chord, you multiply its parts together. I'll color coordinate it for you. Like part A, I'll put this in green, and that will get multiplied by part B. I'll put that in yellow. So the green times the yellow, and then we'll take two different colors. I'll do a red color for C. That red color times this blue. So green times yellow equals red times blue. Really a very simple formula to use. And this actually is true thanks to similar triangles. Now you might not see any triangles in here, but if you connected these two endpoints, you'd make two similar triangles, and this fact would be true as a result of similar triangles. But let's actually try this out, make sure you understand how to do it. It's pretty simple. Okay, so in this diagram we have really the same situation. How are we going to take care of this? Well, we're going to multiply the parts of the chords. Like for example, 5 times 8. 5 times 8 equals 4. In this case, we're missing the x, so it's going to be 4 times x. So we're going to get 40 equals 4x, and x equals 10. So this portion ED is 10. All right, simple enough, right? Okay, the next problem, the diagram is not drawn. So you would have to create the diagram. It says in a circle, so we'll make a circle. It says chords A, C, D, and AB intersect at E. So let me draw that in. So here are two chords. I'll call one chord AB and the other chord CD. And they intersect here at point E. Let's see what the pieces are. CE is 6, ED is 10, BE is 12, and we want to find AB. Well, that's weird, because AB is not part of this formula. Okay, so what we'll do is this, very simply. Let's find EA, and then we can find AB by adding these pieces together. Otherwise, we're going to follow the same formula. You can't do these together as one. You have to do each in parts. So again, setting up our formula, equals 6 times 10 equals 12 times x. So we get 60 equals 12x. We get x equals 5. So basically AE is 5. But then if you want to find AB, we would just add 12 and 5, which gives us 17. So that's how you'd find that whole piece. All right, pretty easy. All right, let's go take a look at the next page. All right, something similar, slightly different. Let's see what this says. It says, in the diagram, diameter CD intersects chord AB at point E. Find the length of chord AB. Now, they're telling us that those two pieces are equal, okay? So they're basically telling us that AE is the same as EB, and therefore that we can find these by using the same formula. A diameter is a type of chord. Same formula. So we're going to do 8 times 2 equals x times x. So you get 16 equals x squared. You know you square root that. X is 4. So each of these little pieces, AE and EB, are 4. So that means AB would be 8. Okay? Okay, so let's go take a look at the next problem. And again, you can try these now on your own. And you can pause the video and you could check it against what I do here. Okay, let's see. We got the same kind of diagram. We got LK is 30. This piece is 30. KM is 10. NK is 15. And they want us to find NP, but first we're going to have to find KP. And then we can add the 15 to KP to get NP. All right, so again, our basic formula here is going to be 30 times 10 equals 15x. So you get 300 equals 15x divided by 15, and you get x equals 20, but that's not the final answer. We wanted to find NP, which is 15 and plus 20, so that's going to give us 35. Please show that work. That's 15 plus 20. Didn't have a lot of room here to do it. All right, let's take a look at this next problem. In the diagram below, diameter CD intersects and is perpendicular to chord AB at point E. Well, this seems similar to that, but there's one important difference here. They're telling you the diameter is perpendicular to the chord. Now, for a diameter to be perpendicular to a chord, it must also bisect the chord. Now, it didn't say that here, but clearly it made a right angle here. But here, it's telling you it makes a right angle, so we know these pieces are going to be equal to each other. All right, let's see what else they gave us. ED is 24, so from here to here is 24. CE is 2. We want to find the length of AB. Each of these pieces are going to be x. It's going to be something like what we had up on top. Let's see what we got. We got 2 times 24 equals x times x. That's going to be x squared, and that's going to be 48. Square root of that. Now here it says to get your answer in simplest radical form, so you're going to have to break that down using the perfect squares. The largest perfect square that goes into 48, why don't you try it? Pause the video, see if you could break that down. It's 16 and 3. So we get 4 rad 3 is what x would be. So x is 4 rad 3. But if we want to find AB, we need 2 of those. It's going to be 4 rad 3 plus 4 rad 3. And that's going to become 8 rad 3, which is the length of A to B. Okay. All right, so now we got a slightly more complicated problem going on over here. A lot of room to work. Let's take a look what's going on. Okay, we got the same kind of scenario. It says EH is 3, HG is 12, and here's the key. DH exceeds HF by 5. DH exceeds HF by 5. Think about how you would set that up. HF we don't know, we'll call it X. And this is 5 more than that, so this is going to be X plus 5. Still, we got the same situation, the parts of chords being multiplied together. So you're still going to do that. So what are we going to get? 3 times 12 equals x times x plus 5. It's going to be 36 equals, you got to distribute this, x squared plus 5x. This is going to be a quadratic equation. To solve a quadratic equation, remember you got to get one side equal to 0. Let's subtract 36 from both sides. And now you got to factor this. Two numbers that multiply to negative 36 and add up to 5. So, you can think of the numbers that multiply to 36. You got 6 and 6. That won't add up to 5. 12 and 3. 12 minus 3 is 9. 12 plus 3 is 15. Not going to be good. You also got 9 and 4. 9 minus 4 is 5. So that's going to be some good numbers. So you got x and x. You got a 9 and you got a 4. Now you got to find the combination that's going to add up to positive 5. You're going to want a positive 9 and a negative 4. Now you do x plus 9 equals 0 and x minus 4 equals 0. This side is going to give us a negative number. Well, we're going to reject a negative number because we can't use a negative length. But this side is going to give us positive 4, x equals 4. So what are we looking for? We're looking for df, but we know that hf is going to be 4. dh is 4 plus 5 is 9. And therefore, df is the sum of these two numbers is 13. So df, that's the answer to this problem, is 13. So that's how you do these types of problems. We're going to take a look at another type of problem next. Okay, so let me open up the other. Okay. Now, relationship between the lengths of two secants. Relationship between the length of two secants. Now, we saw a scenario like this before, but it's not the same. In the past, in lesson, I think it might have been lesson 2 or 3, what we had done in such a case is we were looking for the measure of this angle and the relationship between these arcs, the arcs and the angle. Now we're looking for the relationship between the lengths of these things. And this is, I'll read the fact to you and then I'll explain it in more detail. If two secants intersect outside of a circle, like here at point E, then the product of the measures of one secant and its external segment is equal to the product of the other secant times the external segment. Okay? So basically, the whole secant times its outer part is equal to the other whole secant times its outer part. So this thing would be a whole. And this would be the outside or external part. And here, I'll do it in a different color, also a little thinner so I could fit it. Here, I'll do this in red. Here's the whole, and here's the outside. And this will be the formula you use. You're going to do whole times outside or external equals whole times outside. You got to do both secants and multiply each whole secant by its outside or external part. Don't multiply by the internal part. And you don't want to multiply internal by the inside times the outside. You always want to do the whole times the outside. Let's do a little bit of practice, get the hang of it, okay? In the diagram below, AE, that's the whole thing, is 16. BE is 6. DE is 4, and what's the measure of this whole secant? CE, we'll call it X. This is set up nicely for us. It's the whole times the external part, nothing to do with the internal part, and the whole times the external or outside part. So here we got 96 equals 4x. Divide both sides by 4, and you get x is 24. So this whole this whole secant is 24 units long. All right, let's try another one. Here we have UW is 40, VW is 12, SW is 30, and they want us to find ST. That's interesting. That's an inside part, an internal part. Well, this formula doesn't allow us to find internal parts, so we're going to have to do it in an indirect way. Let's find the external part, the outside part, because the formula provides us for the ability to find an outside part. Let's use the same formula, whole times outside equals whole times outside. Let's plug in what we have. Start with the one on top. 30, the whole times the outside x, and the whole here is 40 times the outside is 12. So we got 30x equals 480. Divide both sides by 30. And you get x is 16. So this part here is 16. But it asks us to find ST. Well, we're going to have to come back and do that now. ST is equal to the whole minus the external part, and that's going to give us the internal part, the ST part, which is 14. So bear in mind that the formula doesn't allow you to use the internal parts, the inside parts directly. You'd have to go about it by doing it afterward like I had done here. All right, let's go look at the next page. Here we're going to have to draw our own diagram. Okay, let's see what we got. It says encircle O, this will be the circle, secants STW, that will be one secant, and UVW, and they'll meet here by W, UVW, so I'll write these S in that row, in that order, STW and UVW are drawn from an external point W. And ST, V, and U are on the circle. Now it says ST is 15, TW is 20, UW, that's this whole thing, is 28, and it wants to find VW. This is weird. This internal part is, inside part is kind of bothering me. We don't do an inside part. We only use the outside part and the whole. Well, you should be able to figure this out. Don't use the inside part directly. Add these pieces together to get the whole. You're going to do whole times outside. This 15 was just to allow you to add them together to get the whole. Otherwise, the formula is the same. It's the whole 35 times the outside 20 equals the whole 28 times the outside, we don't know which is x. We didn't use the 15 in our formula. That inside part is not helpful for us because we don't use that in the formula. So what do we got? This becomes 700 equals 28x, and divide by 28, and you get x is 25. This VW part is 25. All right, you could probably try the next one on your own. Let's see what we got. FH is 18, HG is 4, EH is 6. Find DE. Let's find DE later. First, find the whole, and then you can find DE as in the second part of the problem. So again, it's going to be whole times outer equals whole times outer. So we're going to get 18 times 4 equals x times 6. So 72 equals 6x. X is equal to 12. So to find DE, you would do 12 minus 6. 12 minus 6, DE is 6. Okay? DE equals 6. All right, we got one last thing. It's very similar to what we had just done. It's the relationship between the lengths of a secant and a tangent when they meet at an external point. Okay? So this is how it works. If a tangent and a secant are drawn to a circle from an external point, then the square of the tangent segment, in other words, take the tangent segment times it by itself, is equal to the product of the measures of the whole secant and the outside part. So for the secant, you treat it just like we did before. It's the whole times the outside part. But for the tangent, it has nothing to multiply itself except by itself. So you multiply the tangent by itself. And so let me draw this out for you. This is the whole. This is the outside part. Let me do this in a different color also. This is the whole and the outside part. So technically it's like the same exact formula, except since the whole is the outside part, instead of saying whole times outside for the tangent part, because this is a tangent, you would do tangent squared, multiply a tangent by itself, is equal to the whole times the outside part. Tangent squared equals whole times outside. Okay, now we'll try this problem. We'll try a couple of problems with this, and you'll be good. All right, so let's see what we got here. We got PA is 12, PC is 16. What's PB? So we got tangent squared equals whole secant times outside. Tangent is 12. We're going to square that. Is equal to the whole secant, which is 16 times the outside part. 144 equals 16x. Divide both sides by 16. We get x equals 9. Basically, PB is 9. That's how you do it. All right, if PC is 14 and BC is 6, then find PA to the nearest tenth. Well, it's a little bit weird. We're missing the tangent. That's okay. but the outside part is not given here. What do you think you would do? Well, we don't use the inside part in the formula, but we can get the outside part by subtracting these. And if you subtract 14 minus 6, you're going to get that's 8. And again, you're going to do tangent squared x squared equals whole, which is the 14, times the outside part, 8. That's why I'm putting an arrow to it. Don't use that inside part. So what do we got? We got x squared equals 112. And if we take the square root of that, we get x equals 10.583 dot dot dot. And to the nearest tenth, we're going to get x equals 10.6. Okay, last problem. You could try it. This one they're asking for in simplest radical form. Let's see what we got. BC is 22. PB is 18. We want to find PA in simplest radical form. Remember, we don't use the inside part, but we can add these together to get the whole. And let's use the same formula. Tangent squared x squared equals whole times outside part. X squared equals 720. Break this down. The largest perfect square that goes into a 720 is 144. 144 goes into 725 times, so we get 12 rad 5. That's the length of PA, 12 rad 5. All right, so that's how you do these problems, so work on your homework.